Hello. Today we're going to solve a problem using freezing point depression so that later on, after I go through this, all the steps involved in doing this, you will be able to then do a few problems on your own. And I've taken the liberty of writing the equation up here for the freezing point depression, which basically says the change in the freezing temperature is going to be equal to the freezing point constant times its molal concentration, molality, not molarity, recall that, and multiplied by I, which stands for the Van 't Hoff factor. And this is really only used if we have a ionic solute. So our problem states, determine the freezing point of a solution of sodium chloride, NaCl, and water when 20 grams are dissolved into 100 grams of water. Well, there's quite a few things that we have to either convert or find before we can actually plug numbers in up here. One of the things that we have to find is the molality. Well, we don't even have moles up here, so what we're going to have to do is do little unit conversions. We have 20 grams of NaCl. We want to convert that to moles. We know that 1 mole has 58.5 grams in it. And when we do that, it comes out at 0.342 mole. We also need to convert our grams of water to kilograms, and we should know by now that there are, in 1 kilogram, 1,000 grams, and this comes out to 0.1 kilogram when we do that math. Now we can plug this information into our molality. We know that molality is equal to mole of solute over kilograms of solvent. Okay, hopefully you can see that. I know I write pretty small sometimes. Our mole of solute, we already determined, is 0.342. Our kilograms is 0.1 kilogram of solvent. And when we do this, we figure out that M equals 3.42. Okay, see that? And that's just by dividing these two numbers. 0.342 divided by 0.1 gives us our 3.42. So now, since we have this, we can plug this information in to our equation up here, which I'll rewrite some of this. T sub F is going to be equal to K sub F. The freezing point constant for water is 1.86 degrees Celsius per molal. Our molal concentration is 3.42, and that's a little m there. And then we have a Van 't Hoff factor. Since we have a ionic solute, this will break apart into sodium ions and chloride ions, which effectively doubles this molal concentration. So that's why we're going to have a Van 't Hoff number of 2, because it breaks into 2 particles, doubling that concentration. And when we go through these steps, we get a 12.72 degree Celsius change. Now remember, because delta means change, and this is a change in the freezing temperature. So the actual freezing temperature is just going to be, or the new freezing temperature, freezing point new is going to be equal to the freezing point of water minus delta T sub F. So we know that the freezing point of water, pure water, is 0 degrees Celsius, and we know that our delta T sub F is 12 12.72. So you take 0 minus 12.72, and we get a new freezing temperature of a negative 12.72 degrees Celsius. Okay? So that's for water. Now what if this solvent happened to be something else? Well, like acetic acid instead of water. Well, the acetic acid, it has a K sub F value that would be different. It is 3.9. So what do you think is going to happen there? Is the freezing temperature going to be more or less? Well, there's going to be more of a change, but the freezing temperature is going to be quite a bit less, about twice as much as this negative value here, because 3.9 is roughly twice that of the 1.86. So if we had a different solvent, all this stuff changes. Of course, though, the freezing temperature of acetic acid is not 0. Okay, so let's go through this. If we had acetic acid instead, if we take our 3.9 times the 3.42 times 2, we get a delta T sub F of 26.6. And then we're going to take the freezing point. It's going to be 16.6 minus 26.6. And we get a negative 10 degrees Celsius. Thank you.